Hello and a very warm welcome to our channel. Today, we're going to explore a concept that is absolutely essential to understanding how much of the modern world works. We're talking about electricity, specifically the kind that powers our homes, our cities, and our devices, alternating current, or AC. The specific topic we're diving into is called instantaneous value. Now, I know that sounds like a phrase straight out of a physics textbook, and it can seem a little intimidating at first. But I promise you, the idea behind it is incredibly simple and intuitive. By the end of this video, you'll not only understand it, but you'll see why it's so important. Think of it this way: imagine you're watching a thrilling car race. The cars are speeding up, slowing down for corners, and constantly changing their speed. If someone asked you, how fast is that car going, the answer would depend on when you look. Its speed at the starting line is different from its speed on a straightaway, which is different from its speed in a sharp turn. The speed you see on the speedometer at any single moment, that's its instantaneous speed. Instantaneous value in electricity is the exact same idea. It's the value of an electrical property, like current or voltage, at one specific, frozen moment in time. It's our electrical speedometer. Let's look at the formal definition together and break it down, piece by piece. The first line says, it is the value of AC quantity at a particular instant of time. Okay, first up, AC quantity. AC stands for alternating current. To really get this, let's contrast it with its sibling, DC, or direct current. DC is simple. Imagine water flowing through a garden hose. You turn the tap on, and the water flows steadily, in one direction, from the tap to the nozzle. That's DC, a constant, one-way flow. Batteries provide DC power. AC, on the other hand, is completely different. Instead of a steady flow, the electricity in an AC system is constantly alternating its direction. The electrons in the wire don't just march forward, they rapidly wiggle back and forth. They flow one way, stop, reverse, flow the other way, stop, reverse again, and repeat this cycle over and over. The electricity in our wall outlets is AC. So, when we say AC quantity, we're talking about an electrical property like current or voltage that is part of this ever-changing, alternating system. The second part is at a particular instant of time. This is our pause button moment. Because the AC quantity is always changing, its value is never the same from one moment to the next. So, to talk about its value meaningfully, we have to pick a single, tiny, frozen slice of time and ask, what is the value right now? That right now is the instant. The next sentence says, the magnitude of the waveform as taken at any point of time is called instantaneous value. This sentence adds two more important words, magnitude and waveform. Magnitude is just a fancy word for how much or how strong. It's the numerical size of the value. A waveform is simply a graph, a picture, that shows how something changes over time. And that brings us to the graph on the screen. This graph is the perfect visualization of an AC waveform. It tells us the entire story of our alternating current. The vertical, up and down axis represents the current, which we symbolize with the letter I. Current is the actual flow of electricity. The higher up we go on this axis, the stronger the current is flowing in its positive direction. The zero line in the middle means there is no current flowing at all. And if the line goes below zero, it means the current has reversed and is now flowing in the opposite direction. The horizontal, left to right axis represents time. As we move from left to right along this line, time is passing. So, this graph lets us see exactly what the current is doing at every single moment in time. Now, for the star of the show, this flowing curve. This shape is called a sine wave, and it's the natural pattern that most AC power follows. Let's take a journey along this wave. We start at the beginning, at time 0. The wave is on the zero line. This means that at the very start, there is no current. As time begins to pass, we move to the right, and you can see the wave starts to curve upwards. The current is smoothly increasing, getting stronger and stronger. It keeps rising until it reaches its peak. This is the absolute maximum strength the current will have in this direction. The moment it hits the peak, it starts to curve back down. The current is now getting weaker, decreasing in value, until it crosses the horizontal line again right here, at the point labeled pi. At this moment, the current is back to zero. It has completed the first half of its journey. But the journey isn't over. The wave continues, dipping below the zero line. This is the alternating part of alternating current. The current has now reversed its direction. It gets stronger and stronger in this new, negative direction until it hits a negative peak down here. From there, it starts to weaken again, curving back up towards the zero line, finally completing its full cycle right here at 2 pi. It's now back where it started, at zero, ready to begin the entire cycle all over again. This entire up and down journey happens incredibly fast, usually 50 or 60 times every second. So, where does instantaneous value fit into all this? Look at those red vertical lines. Each one is a snapshot. Each one is a measurement of the instantaneous value. Let's say we press our imaginary pause button at the first moment in time. We measure the height of the wave. That height is our first instantaneous value, which is labeled I1. It's a relatively small positive value. We let a tiny bit of time pass and press pause again. The height of the wave is now I2. As you can see, I2 is bigger than I1. The current is stronger at this instant. We continue this process. At the next instant, we have I3, which is stronger still. Then I4, I5, and I6. Each one is the specific value of the current at that specific moment. Around I6 or I7, we're at the peak of the wave. This is the peak instantaneous value, the highest value the current will reach. Then, notice what happens. At instant I8, the value is a little lower than the peak. At I9, it's lower still. And by the time we get to I10 and I11, the instantaneous values are quite small again, as the current rushes back towards zero. This is the core idea. All of those I's are individual instantaneous values. They are not the average value, nor are they always the peak value. They are simply the value of the current at whatever moment we choose to look. Now, this whole concept applies equally to both current and voltage. Remember, voltage is the electrical pressure or push that makes the current flow in the first place. It also follows a sine wave pattern in an AC system. To keep our work neat and consistent, engineers and scientists use a standard notation. The instantaneous value of current is always represented by a lowercase I. And the instantaneous value of voltage is represented by a lowercase v. When you see these lowercase letters in electrical formulas, it's a signal that you're dealing with a value that changes with time, not a fixed or average value. So, let's tie it all together with our car race analogy one last time. The peak value of the current is like the car's top speed, the fastest it can possibly go. The average value would be like the car's average speed over the entire race. And the instantaneous value, Ri or V, is the speed you see on the speedometer at any single moment you glance at it. It could be high, low, or even zero. Understanding instantaneous value is the first major step to truly understanding AC circuits. It allows us to analyze, predict, and engineer the systems that power our lives, second by second, or more accurately, microsecond by microsecond. I truly hope this detailed walkthrough has demystified the term instantaneous value for you. If this explanation helped you, please consider giving this video a thumbs up and subscribing to our channel for more deep dives into the fascinating world of science and engineering. And if any part was unclear, or if you have any questions at all, please ask them in the comments section below. We love hearing from you. Thank you so much for your time and curiosity. Until next time, stay curious.